I've got a lot of slides, and I'm going to move reasonably quickly because I'm trying to know something about strategy. I will say this is work. This is kind of a agglomeration of papers that I've been working with Andy King, and then more recently Tim Simcoe. It's kind of exciting, a little bit disheartening, and there's some room for optimism. So hopefully that'll be a good thing. Okay, so Sir Francis Bacon pointed out that human understanding of its own nature is prone to suppose the existence of more order and regularity in the world than it finds. Sometimes this can be pathological, and we call that apophenia. So if you go and you go and psychiatrists will diagnose somebody with apophenia, which is the human tendency to seek patterns in random information. Right? We also have another word for that, more colloquial, which is delusional. So Andy and I coined this term scientific apophenia, which is one of the worst marketing efforts ever, and which is the assigning of inferential meaning when limited statistical power should prevent such a conclusion, or when the data are actually random. So when do we see patterns and make meaning out of the data? When when the evidence really isn't sufficient to allow us to do that. So is this a big problem? So let me show you a thought experiment. This is from Annie and my papers. But it's a very simple Monte Carlo experiment. So generate a random y and x. So it's completely random numbers. All right, let's say we have 100 of them. And we're going to explore 4 permutations of y and x, relationship between y and x. So the first one is y equals beta x, very simple model. And then we're going to try log of x, because maybe we ran the regression on x and we didn't get a good result or a significant result. And then we're going to try x squared. All right, so now this kind of adds this twist that what was negative is now positive because it was centered on 0. Right? And then we'll try 1 over x because maybe we had misconstrued the data generating process altogether. And so maybe that's the right regression. So if you look at that, and if you look at any one of the p-values on each one of those, we should see them randomly. The p-value should be below 0.05 5% of the time, because that's what 0.05 means. And we're going to go, but we're just going to stop when a significant finding is found. So if we go and one of them is significant, we're going to stop the process. We found our result. Now we can publish this wonderful relationship between y and x. So when you run this 10,000 times, this is the distribution of t-statistics that you find. Right? And you can see that there is there's a blip around 2. And if you look at it, we should see greater than 2, or 1.96 technically. We should see that 500 times, but instead I find that 1,781 times in this particular this particular simulation, or about 18%. And I find fewer right near 2, because what's happening is some of them are getting nudged over the border. So I should see 500, and I see only 431. And then the insignificant ones, I should have 9,000, and instead I only get about 7,800 or so. So now I've got a problem. Well, that's a theoretical problem. This is a thought exercise. So the question is this a real problem? Does it matter in the field? So if you look at 300 cited articles, is this a problem in strategy? So here's 300 articles from 5 top strategy journals from 2002 to 2012, and you see a very similar spike right around 2. So that's a problem. And what you also don't see, interestingly enough, is you don't see enough published results that are close to 0. So we're not publishing our nulls, and we're moving things over the boundary. So Bacon was right. 3 and 5 results will replicate, and 2 and 5 will not. If we actually go and do a repeat test and draw from the same sample, that's what we'll find. So then the question is, can you solve this problem? So now we have a scientific apophenia problem because we're drawing conclusions when it looks like there's often noise. So will replication solve this problem? So let's first think about, well, what are the causes of scientific apophenia? How does this happen? So the first, Rich Bettis points out, is we sift through databases and we look for significant results, searching for asterisks. And I'll ask Rich again, I don't know why he didn't call it searching for stars as opposed to asterisks, because I think that's a better name, but that's a different problem. We p-hack, which some would argue that these are very similar, but I'm using the very narrow idea, which is just nudge samples. So I'm very close to 0.05, and I'm just going to find the right specification to get it just over the boundary. We have other problems that are equally as important. One is this availability. If something is published, it is true. And this belief that once it's published, we give extra weight to that particular publication. And you see that comes out with statements like, we know theory X is true because of and it's proof by citation. Right? These are all, I'm going to argue that these are all manifestations of Ed Leamer's forking path problem. So let's kind of unpack that claim. First, let's consider what an estimate is in the first place. So if we get an estimate, there you go. We've got a distribution of our test statistic. This might be a t statistic or a z statistic. And we have a value, say that's 2, right? Just significant. And there's a distribution around it, because that's what a statistic is. But we might have actually drawn that value from a different distribution. The first one I showed you was simply our best guess. But that doesn't mean that this isn't unlikely. In fact, there might be, say, a 1 in 3 chance that this was the right distribution. Or maybe that one. This sort of draw where you get a really high number from a distribution whose mean is way shifted to the left, this would be a false positive, say. Right? But only with replications can we know which one is right. So we'll keep drawing, and eventually we'll get a pretty good estimate of that distribution. And that's why, that is the idea behind replication. That is why replication is a good thing. The hints of the problem are already here, because the theory requires that we draw another draw. We draw from the same underlying population. And in most archival research, in the study of industry, which strategy often is, that's a really hard thing to do. Okay. But when you only have one estimate, you really don't know what you have. Let me show you some simple regressions. Here's one regression, and if we interpret that regression, most people would say there's no effect. Okay? That is a t statistic underneath, and you've got a correlate. You've got a point estimate and a 0.89. It's negative, no effect. But if I draw that one, I've got a positive effect. So now, if I'm relating y to x, n equals 100, now beta is something. I've found evidence in support of my theory, but it's barely significant, but it's pretty good. And here's one that's, I've got a t-stat of 0.79, coefficient of 1.59, not so great. Right? And here, that is my result. I'm taking that one to the bank. Right? 3 stars. There's 3. And we all know that 3 is bigger than 1. right? So that's a really good result. Now, the truth is that beta equals 4. And I know beta equals 4 because I created the data generating process, and this is a simulation. So I know for a fact that the true value is 4. What's really interesting is the value we're going to like the most is going to overstate the power of my theory. Right? But they're all consistent, and we see that when we look at the confidence intervals. Notice that all these confidence intervals overlap. So while there are problems comparing coefficients across regressions, the first guess is showing complete consistency across all these results. And of course they are consistent because they're all driven from they're all drawn and generated by the same data generating process. But when we run a study, we've got one draw, and we don't know which one we have. And so we have to figure out how to think about that in the context of how we do our research and the way we write. So, and if we can replicate, we'll know this, right? And indeed, the SMJ, perhaps one of the leading, the premier or the leading strategy, one of the leading strategy journals, has changed their policy about replication. You can now, they actively solicit replications. If you go and try to submit an SMJ paper, it will ask, is this a replication paper? Do you want it to be evaluated as such? So, and we're trying to do what experimental scientists do, right? Which is get the same draw from the same distribution, from the same underlying population. Right? And sometimes social scientists can get pretty close to this. There are over 50 reasonable papers that think about unemployment and minimum wage. And we have some reasonable ideas about what these effects are within certain parameters. But you can aggregate. So that's good. Can we do it in strategy? So let's replicate. So here's an example of a replication. This is a paper by Huggy Rao from 1994. And it is very clearly titled, The Social Construction of Reputation, Certification Contest, Legitimation, and the Survival of Organizations in the American Automobile Industry from 1895 to 1912. Okay? And the paper makes a very simple idea, takes a very simple argument, and says we have this, if you're a young industry and you're a new firm, you have to find a way to convince customers and investors and other resource providers to either invest or buy your product. So you have to, so the argument is you have to legitimize yourself as a firm, which means become taken for granted as the firm that produces, or one of the firms that produces this product. So how should you do that? Well, through a contest. If you win a contest and you're at the best at doing this, that's going to be a good thing. So, so we've replicated this, and this is good. So in Rao's original paper, he gets a coefficient excuse me, that's not a coefficient, that's an odds ratio, but of 0.4. And in our replication, we get 0.46. Now we're drawing from the same data source. So we should be pretty close. And I feel very comfortable saying that the fact is there is a correlation between the number of victories over time that a firm aggregates and their probability of survival, and it is positive. And so I can say that is a fact. Okay. Should we claim victory? Are we there? I don't know. Let's think about what we mean by replication, what replication can teach us, and we'll revisit this. So this is taken from Helfet, Bettis, and Shaver, and this is, it's Bettis, Helfet, and Shaver. Sorry, Rich. And what they do is they adapt this Tseng and Quan piece, and they think about different types of replication. So you can have the same data in the same measurement and analysis, and that's what you would call a checking analysis. So if I publish my data and somebody finds an error, it's going to fit into that upper left-hand box. Okay? So the controversy over this time is different was precisely in that box. All right. But if I have the same population and I do the same technique, so now I'm just drawing another sample from the same population, they're going to call that an exact replication. But then you start getting into but now we're moving outside the statistical theory a little bit. Because if I have a different population, well, that's an empirical generalization. I found that a fact was true for biotech firms. Now I'm going to see if it's true for nanotech firms. What if I have different measurement and analysis? So instead of asking whether a company survived, whether an early auto firm survived, maybe I should ask, did they lead the industry? Were they profitable? That would be an example of a different measurement and analysis. Or maybe I want to start thinking about some sort of generalization. Well, if legitimation is a real applicable theory, maybe what I should be doing is I should look for different contexts and settings in which I think that might apply and see if I see evidence of it there. Now, that's not quite replication, but we would consider, according to Helfat et al., this is going to be, or Bettis et al., that's going to be an exact replication. And anything where you start really flipping out the data or flipping out the measures, we're going to call that a quasi-replication. Now the problem, each of them are subject to different problems, all related back to Leamer's forking path problem. By the way, I had done somewhere between these two things, either a same data, basically an exact replication. Okay, so let's go back to the theory and let's think about what the problems might be. So Rao's theory is that you were first place in car races, right? So you did some sort of certification contest, a rank order one. Right? This created cognitive validity, legitimation. Now you're taken for granted, and now you have reputation as a firm. Because you have reputation in other people's minds, that's why they give you resources and you survive. That's the theory. Okay? The fact is, if you finish in first place, or the more you finish in first place, the more likely you are to survive. And that's what the replication is too. In fact, the replication is a little bit more nuanced because we can show that all you had to do was participate, and that's just as predictive, but that's a different story. Okay, so just keep that in mind, because we have to translate those blue boxes to the orange and gray ones. All we have learned that conditional on that translation, it appears that the correlation is real. But the key thing is it's conditional on that translation. So with an exact replication, we can evaluate whether the same correlations are in the data, but exact replications do not fix any study design problems we may have. Okay, so let's back up and think for a moment. It's a recursive talk. We're going to back up and we're going to think for a moment what it means to know something. So there's this theory of justified belief, a theory of knowing. And so the idea is that something is true, P is true. And then you have a belief that you believe P is true. S believes that P is true. And then it's going to be justified. And justified means, well, we'll get to it in a second, but the idea is you're justified in believing that P is true. Okay? But what is justified? Well, we want something to be reliable. So the idea is if it's true today, it'll be true tomorrow. Okay? That's the basic idea. We want it to be sensitive. Right? So if we start changing parameters, it makes reasonable predictions. Right? And we don't want it to cause danger. Right? We want it to be safe. And we certainly don't want just epistemic luck, which means we have an explanation that happens to be predictive, but is probably wrong. So there's a recent paper by Simmons et al., and they show that they show correlation between listening to the Beatles song when you're 64 and your age. And it turns out that if you listen to the song, you're older. Well, that is something, it's a belief. It's justified because it's supported by statistical evidence, right? But it was just lucky. It doesn't have any real validity. And sometimes we like elegant theories, theories that make us feel good about the world, regardless of whether they're true. Okay? So we want to get rid of virtue-based justification. But that exists. All right, so we've got this idea of what it means to know something. We're going to justify it. And how are we going to justify it? Well, we have ideas about how to do that. So the first one is Popper. So Popper says that useful theories are things that haven't been ruled out. I have a theory that when I jump out of a parachute, the anti-gravitational force of silk prevents me from falling quickly. I can run an experiment and eliminate that theory, but until I do, it hasn't been ruled out. Okay? Note that Popper is very careful. He doesn't have true and false theories. He has useful and not useful. So they're useful if they're predictive. So when you read in a paper, show, or you make a claim that something is true, that is in and of itself not Popperian. Neiman Pearson have a slightly different way of doing this, and these are related. They'll have a horse race. We have two theories, H1 and H2, and we're going to compare the confidence intervals of the tests, the statistical tests that come out of those predictions, and the better fit is going to be a good guide. Notice that they're not using true and false here either. Now, the good thing about Neiman Pearson as opposed to Popper is when we operationalize Popper, we often use nulls that are kind of stupid. I think that's the technical term. But the idea is we'll come up with a null that there's no effect, which in most cases is not a very interesting null to begin with. Okay? And then the Bayesians will do something a little bit different. They'll use the information very efficiently, and they'll come up with a specified prior. And then they'll update their beliefs based on their prior. And in some sense, we're all kind of Bayesians. All right? That's why when I told you the story about listening to a song and how that might affect your age, your priors are so strongly against that that you will reject basically any evidence I give you for it. Right? Right. One of the problems is it does require this ex-ante specification of the underlying probabilities or your priors, and that's hard and sometimes arbitrary. So let's think about what we actually do. We start out and we say that A is probably related to B. That's our theory. Okay? Put it up there like that. And we find, this is the very simple way, we find a correlation between A and B. Some sort of statistical association. Right? And then we conclude that A causes B. Or perhaps A is stochastically related to B. So if we see A, we're more likely to see B, as opposed to a direct causal effect. But that's the basic framework of how our reasoning often works. It's a little more complicated, and let's unpack that. So in an example, here was our A. If you first places in a race, then you get cognitive validity and reputation, and that led to resources and survival. Okay? Found my correlation. Here's my correlation right there. Therefore, first places in race leads to cognitive validity, and hence reputation, and resources and survival. And that is how the reasoning actually worked. Okay? Exclamation point. Okay, well, let's unpack it. You know, if we're a little bit more careful, we might say that on average, this is what we see. Because statistical regressions, most methods are about averages. right? And then we're going to have some social or behavioral mechanism that is that arrow. And that was this legitimation argument that Rao put forward in that example. But we have other theories, right, which we use, which are tons of theories. Right? And then we have H naught, which is there is no relationship. Right? That's our null. But it's often really hard to measure A and B. I don't know how to measure legitimation. I don't know how to measure reputation. Very difficult things to measure. I certainly don't know how to measure that for an automobile company from 1904. Right? So I have to come up with a proxy. And so I say that, well, I've got C, which is related to A, and I've got D that's related to B. So that's pretty good. And then I find that the probability that C and that correlation is 0 is less than 0.05. That's I failed to reject the null. Therefore, A leads to B. And that is what we do. When you see I failed to reject and therefore my theory is true, that is what you're seeing. Uh-oh. Now, the other problem, which we saw in the beginning, is that 0.05 is distorted. That was the apophenia. That was the graph with that too big of a mass around 2. So that's already troublesome. Okay, but then it's even a little bit more complicated because, we had C, but really maybe C2 is a better measure. I don't really know how to measure reputation. I can come up with 10 measures. So I'll choose all 10, and I'll pick one of them that I think works the best. And of course, D is the same thing because, well, it's survival, but maybe I want to measure profits, or maybe I want to measure geographic expansion. Right? Maybe I want to measure acquisitions, different measures, different things we can do. Right? And then I'm not really sure about the model, because theory says that there might be some relationship. It doesn't tell me the functional form of that relationship. And so I can come up with some explanation that maybe it's quadratic, maybe it's cubic, maybe it's logged. I don't know. So, and then I don't really know which interaction terms. So I've got some f there that I've got to assume. Right? And then, so I wind up asking whether ci is related through my function of dj with some sort of assumption of f, and really what I have is a bunch of forking paths. So I have to make these choices, because otherwise I can't measure anything. So I choose A1, and I choose B3, and I choose that F1, and if I were just choosing these things randomly, that's great. But that's not really how it works. That is the forking path problem that Ed Leamer wrote about 40 years ago. But here's the thing. I'm working in data that I don't fully understand. And that's natural because I'm working in an archival setting of an industry or whatever setting. And because when I start out, there's no way I can understand exactly what I'm measuring. I have to look in the data set. I have to look at the measures. I have to see how they're constructed. I have to test and see whether the way they're constructed behave in ways that seem reasonable. Because if not, what if it's just noise? But here's the problem. What if it's just noise because that was my draw? So I wind up selecting on measures that seem to make sense based on my priors. So my path in choosing the forks that I choose are non-random. They are chosen for particular reasons. And when I do that, I undermine the meaning of the standard errors. Because the standard errors assume a random draw from a population. So here's the consequence. I explore many C's, and I wind up reporting the good result, Ci and Cj. Right? And the 95% confidence intervals are not really 95%. I do have constraints, so it's not all it's not all just me going out in the world and making stuff up, hopefully. Right? So let's think about what this is. So I've got my social behavioral mechanism there's theories that are better than worse. And you saw that with the, if I try to publish a paper that if I pray in this room and somebody in India gets better and they don't know that I'm praying, it's going to be hard to publish that paper, and for good reason. Right? So that's not very good theory. Right? But at the end of the day, I can never really know if I've evaluated and thought of every theory. That's epistemological uncertainty. And if that other theory is right or a better predictor, then my conclusions are off. And I have no way to evaluate that. That's not in my data. Okay, so we talked about our H naughts. We suck at that. Talked about that. Right? But I'm going to use judgment to find appropriate measures, but in part that's informed by the data. So I'm using up my data to choose my measures. Now I'm going to interpret that F a little bit more generally than just the functional form. There's methods that I can use to present my results. Tim Simcoe has a beautiful web page where he talks about empirical etiquette. And it's just all about how we should report our results in a way that's transparent and disciplines our thinking. So there's constraints on what we're allowed to do. He talks about endogeneity and thinking and that sort of thinking. Right? And then we have to think about how we report the results we find. Are we actually humble in how we report our results? Do we take into account the litany of problems that I've just articulated when we report what we find? So, but understanding the context, I want to be a little bit charitable to our work because it's just such an understandable problem. So the strong version is called harking. Harking is hypothesizing after the results are known. Another word for that might be calibration. I calibrate my theory to the data. And that's clearly problematic. That's just pure p-hacking. Right? But inductive theory building is essentially harking. And so it has room in our world, or we should have room in our world for this exercise so long as we're explicit that we're doing it. Because how else are we going to generate theory if we don't look at the world? The weak version, and this I think this is something we have to do with every study, is we have to clean our data, understand, stop when the measurement kind of works, right? Choice of measures. So that is the weaker version of harking. Okay. So we can replicate, and that's good, and start exploring the robustness of our results to different assumptions, right? But that's really hard to do. Replications take time and a significant amount of time. And they can't simply be pawned off to graduate students because graduate students are learning. So they need a lot of expert guidance, especially in the beginning, and that takes up a lot of faculty time. And if the rewards aren't sufficient, we're going to have a problem. We're never going to start moving down. We're not going to get anywhere. So SMJ changed their editorial policies. That's good. Right? But once we think about the forks, we have a more fundamental problem. And that is when we do an exact replication, it's the same forks. So we're not evaluating robustness to different forks by definition. That's what an exact replication is. And here, if we do a quasi-replication, the exploration of the data is distorting our standard errors. When we go to a new setting, we have to learn about it, and the process of learning about it distorts our standard errors. Okay. Another way to think about this is we can think of quasi-replication as a form of abduction. So abduction is calibrating our explanation to the data. A great example of this is noticing that Africa and South America appear to be part of a jigsaw puzzle. and we can fit them together. So I now have a theory that they were literally once together. Now, how would we test that theory? There's multiple ways, but one abductive way is look for other predictions of the theory. So one prediction is to look at the geological histories on both sides. And if we see that they're similar and then they diverge as the continents moved apart, that would be an alternative method with alternative data to test or evaluate the usefulness of the theory, which became tectonic plates. That is an example of abduction. Well, I'll give you another one. Right? So I have a paper with Anne-Marie Knott. Actually, it's not really a paper. It's an almost paper. It's a finding. And here's the finding. Well, the first one is not my finding. That's Anne-Marie's. And that is a finding. There's a high research. She defines this the efficiency in which one uses R&D money and how that translates to value in the stock market. And she finds that an annually rebalanced portfolio of high research quotient firms, or RQ firms, outperform the S&P 500 by 8x. So that's a big number, and then we're in the world of finance. A nice book about it. Now, our finding, and this is true, is that high RQ is negatively related to citations. The patents of high RQ firms in chemicals are negatively related to academic patents. This result surprised us. It was contrary to our priors. So now we have to figure out, does this mean something? One option is it's a random result. Another option is that academic research isn't useful in chemistry during the time period we're studying. Another option is that the academic research is being commercialized by firms that aren't in the S&P, that are not public firms, for which the RQ measure doesn't exist. We don't know the answer. But all of those would have different predictions, and it's our job now to go to the data and try to adjudicate which explanation is best. However, that is an abductive exercise. But in so doing, we're going to have to learn our data, and we're going to have to use it up. So presumably what we'll do is we'll do that in chemistry, and then we'll go look and see, does the theory and our predictions also hold in electronics? Does it hold for European firms? Does it hold for Chinese firms? And we can look and see if the predictions replicate in different settings. Now here's a case of failed abduction. So in Rao's original paper, he showed this result of 0.414. And then he said, well, if legitimation is happening, then what we should see is that the effect should be larger for startups, because it's more important to establish reputation when nobody knows you. And so in that case, winning races, if that's what's generating reputation, should really matter for startups. That is abductive reasoning. And that's great. Now, he didn't find a result that's a standard error, and it's an odds ratio, so 1 is essentially no effect. Right? So there's not enough evidence of an effect. In fact, it's very noisily measured. It could be small, it could be large, we just don't know. Right? So we have to look at our evidence very carefully. Now, abduction never stops because it uses up the data. Every time we abduct, we have to go into a new setting and learn the data. To the extent that these settings are similar, this problem diminishes. But when we go to a new setting and we use a new measure, because I don't know how to use the racist setting in a different industry because it's idiosyncratic to the automobile industry. And it was chosen because perhaps it was the best measure for the automobile industry. But it doesn't translate. So every time I go someplace new, I have to translate. And that uses up my data. because I'm only going to choose something that seems to make sense and fits my priors. Okay. So exact replications don't solve the epistemological problem. Quasi-replications use up data, so standard errors are distorted. So here we've got this replication solution that doesn't really work. Makes some progress. It's not like it's useless. I don't want to make that statement at all. But it doesn't solve our problem. It's not so simple. So what can we do? Well, we don't have an easy solution, but we have some partial ones, and they're pretty cool. The first one is transparency. Show your paths so that others can evaluate the choices you made. Publish your data. Publish your code. Maybe you made a mistake. Anybody who's coded has made a mistake coding. I guarantee it. You're not unique if you've made a mistake. You're not a failure. You're human. In fact, there's something weird about you if you haven't made a mistake. Right? Now, you can't always reveal your data because sometimes it's proprietary, and sometimes the only way to get it is to promise that it'll remain confidential. But if you do that, that's diminishing the verifiability of your work, and that's diminishing its value. It's worth less because we can't really verify that what you're telling us is true. Not that you're lying. Maybe you made a mistake. Oops. Okay. Principle number 2, explore your forks. Right? We have to make all these decisions. How robust are our results to these decisions? Are we robust to different measures? So some fields do a pretty good job of thinking of reasonable robustness checks. Some don't. Right? But we can, in all, we can do better. So Leamer, from 1978, talks about extreme bounds analysis. He says, let's do every robustness check. Let's take every alternative measure. Let's see how our results change when we include and exclude controls. And let's do every permutation and report the distribution of the betas of the coefficient of interest. Now, of course, not every one of those permutations is going to be reasonable. But it's going to give us some bounds on what we should expect. And we'll know whether what we got is conditioned on the assumptions we made of what to include or exclude. And that's progress. So here's a super simple example. We're going to test x1, and I'm going to regress it with 3 different controls, and I'm going to report the distribution of those 3 betas. I'll report all 3 betas and say, does it matter what I include and exclude? But Leamer is a little bit more sophisticated than that. Right? We can do that in terms of all the different measures. We can do that in terms of functional forms. And then that conclusion might be just a bit more justified in the philosophical sense. So that's good. That's progress. Principle number 3, split samples. If you have a large enough data set, you can do an exact replication in your own study. It's the coolest thing. This is what Fisher was talking about when he brought up the idea of replication. So it solves the using up the data problem. I use up my data to generate my first set of results. And then I go to a clean, new data set that no one's ever touched, that comes from the same data generating process, that is another sample from the same underlying distribution. And if I find the same thing, 1 out of 20 that I should find the same thing. Now you have to be really careful. You can't then, when you don't find the same thing, go back and recalibrate your theory because now you've distorted the exercise. Or if you do that, maybe that's okay so long as you're very transparent that that's what you've done. Because you've got good evidence about that first theory, and the second explanation you come up with is now theoretical more than it is empirical. But that's okay. That's progress. That's abductive. Okay. But there's some problems. you do need lots of data, and sometimes you have small samples. And if you've got a small sample, that's okay. That doesn't mean you shouldn't analyze a small sample. We can learn from small samples. You just have to be, we should be clear about what we can really learn and what we can't. Okay, and the third one is be humble. The identification revolution has come. The replication revolution is here. People are aware of p-hacking. And these ideas are going to become more and more prevalent in our journals and in our work. So we today can write in a way that anticipates where we're going to be. All right? We can skate to where the puck's going to be, not where it is, to almost quote Wayne Gretzky. Okay. Now, you can think of every paper as being somewhere on the spectrum between theory building and theory validation and testing. Every one of our papers, be they empirical or theoretical, are somewhere on that spectrum. And we should recognize exactly or have a good idea where we are. So first thing, anticipate that you got the odd draw. So, and expect other people to replicate and be happy when they do. At least you're interesting enough to replicate. The worst thing that can happen is somebody replicates your paper and it gets rejected because nobody cared about the paper in the first place. That's not a compliment. Okay. So this is a famous philosopher, Ed Parker, Starsky and Hutch. The humble man makes room for progress. The proud man believes he's already there. And my other famous philosopher, Bart Simpson, right? One result is a curiosity. That's really Fisher that said that, Ronald Fisher, but nevertheless. Okay. And keep in mind Leamer's critique. I used up my data generating these results. Okay. Now, we should mean it. So report those forking paths. And here's some phrases you can use. This is only one sample. Future work will be needed to generalize. We need to be cautious in drawing strong conclusions without future research. The results are most suggestive of result X, but more research is needed. Let me give you some more explicit examples about how to write these things. Do not write, we have shown that X is related to Y. Correct, X is related to Y. In this particular sample, generalization will require replication. Author X has shown that theory Y is true. Correct. X found a correlation which they judged as evidence supporting their theory. The correlation was in industry X at time Y. There are other potential explanations. Our results contradict Y's findings. No. Correct. Y's findings appear different. But this may be due to chance. And note that this is more likely in a small sample study. So here are the 4 principles. Transparency, report paths, explain judgment, share your data and code. Number 2, explore paths is report paths. Explore paths, robustness, and you can use extreme bounds analysis. There are canned routines that will do extreme bounds analysis for you. Better in R than in Stata. But still, even in R, even in Stata, there's something, you can do some basic extreme bounds. Split your samples where possible. Right? And most importantly, often you can't do these things. But be very humble and future-proof your writing. Expect and welcome your ideas being challenged and overturned, because that is a scientific process. Thank you.